appreciate that. And I do want to welcome you to our first, lecture in our series. We've never had that before. We call it Engineering in Action series. So it's a new forum. I'm not sure who came up with this, but it's a great idea. And you know that we get a lot of visitors all the time. People come in visiting our buildings, our labs, the community at large, not just the alumni. And so we don't get that anymore. So we wanted to be able to do something different, and we wanted then to reach out to you and you to get to see what we're doing in the School of Engineering. And of course, it's COVID time. However, it's also Zoom time. So thank God we can do some new amazing things that we couldn't do before. So we do hope to keep that series going because we got a lot of things, great things that are going on in the School of Engineering. And this is an opportunity to showcase a lot of our faculty and what they do. So I'd like to start. We're going to start first with Christina Salas. Christina Salas is not just a faculty, is a super faculty because she's a faculty in two colleges. She's a faculty in the School of Engineering. She is an engineer, and she also has an appointment with the medical school, so she understands that world there. So for us, we're very lucky to have Christina Salas to be the liaison. So when this COVID came in, we were a little bit confused. Everybody wanted to print 3D printed stuff, and we didn't know what we're doing. I said, everybody get out the picture, let Salas lead it. And indeed, she led this effort, and she'll talk about it today. But we wanted to showcase, to start this series with our brilliant faculty, Christina Salas, one of a kind, who made us look really, really, really good with her mask production. So with that, again, I want to welcome everyone. I want to thank everyone, and I want to thank Christina for taking the time to do this. So that's all for me.
Thank you, Dean Christodoulou. Good afternoon, everybody. My name is Mariah Paiucci-Lee. I hope you're all having a wonderful Friday. I'm a senior here at UNM studying chemical engineering. It is my pleasure to be the host for today's Engineering in Action speaker series with Dr. Christina Salas. As mentioned, Dr. Salas holds joint appointments at UNM. She is a faculty member in both mechanical engineering and in medicine, but specifically the Department of Orthopaedics and Rehabilitation. Dr. Salas is also the Special Assistant to the Dean of Engineering for Health Science Relations and has recently been named a Badass Woman by InStyle magazine. She is one of 50 women recognized for their heroic work in healthcare. Today, Dr. Salas will share with us how her engineering and medical knowledge led to her current work in orthopedics, as well as her efforts producing PPE for critically needed areas in New Mexico. But before we get started, I want to mention we do have a time reserved at the end of the talk for a question and answer. So I encourage you to use the chat function for your questions. It is now my pleasure to introduce Dr. Christina Salas.
Thank you. All right. Share my screen here. All right. Thank you very much for that introduction. Thank you, Dean, as well. So I was asked to speak about quite a few things today, and honestly, each of the things that I was asked to speak about, I could probably talk for about 40 minutes for each one individually. So I'm just going to go ahead and get started. As Mariah mentioned, there'll be a question and answer session at the end, and I will do my best to stay on time. So again, my name is Christina Salas. I'm an associate professor, and I bridge both sides of campus between the Department of Orthopedics as well as the School of Engineering. A little bit about myself. I was born and raised in San Antonio, Texas. I got my Spurs and the Riverwalk up there on the screen. I received a bachelor's degree in mechanical engineering at California State University in Chico, California. This is in Northern California, just north of Sacramento. And then I moved to New Mexico and I received my master's in mechanical engineering here at UNM. During that time, I was actually fortunate to get connected with the Department of Orthopedics, which is the department who actually supported my master's research in biomechanics. And when I finished my master's in mechanical engineering, I knew that I wanted to take my mechanical engineering knowledge and apply it to medicine. And fortunately for myself, at the time, the School of Engineering had started a graduate program in biomedical engineering, and I was able to enroll as one of the first students. I was actually, I think, the second graduate of the biomedical engineering graduate program. During my time in the program, I also acquired a minor in the nanoscience and microsystems engineering degree program. And while I was in that program, I received an NSF IGERT. It's a research and traineeship that actually supported 2 years of research that I could do anywhere I wanted to. And so I was fortunate to do 1 year, almost 1 year of my research at the University of California in San Francisco, specifically at San Francisco General Hospital in their biomechanics lab, doing experimental biomechanics. And then the second year of my funding, I received a pre-doctoral position at the Mayo Clinic in Rochester, Minnesota. And that was some experimental biomechanics, but it was mostly computational biomechanics and finite element modeling. And they were nice enough to actually support me for a second year on that. So I actually did 2 years of experimental and computational biomechanics with the Mayo Clinic before I came back to finish my PhD studies and moved on to my current position. So what I'm going to do today is I'm going to very quickly provide an overview of two of the core research areas that I work in, partly because this is such a broad audience and not many people have, those people who have heard my presentation on the mass don't really know much about what I do with regard to research. And also because I'm trying to encourage some students that might be, undergrads or grads in some of the core engineering programs like mechanical, electrical, computer science, to maybe find some interest in biomechanics and biomedical engineering, because my lab is very interdisciplinary and I'm always looking for new students to help out with a number of these projects. One thing I should say real fast is that there are a couple of pictures in here that are a little bit gory. I will do my best. They're actually they've been consolidated. They're kind of in just the next few slides. So if you don't like to look at that stuff, feel free to look away. So first of all, I run the Orthopedic Biomechanics and Biomaterials Laboratory. We call this the OBBL. This is on the North Campus in the Health Science Center. And in this, it kind of speaks for itself. We basically do tissue scale biomechanics and a number of biomaterials engineering projects. Essentially, our research covers a lot of areas. So everything from pediatric research, every type of orthopedic subspecialty that you can think of, joint, sports medicine, hand and upper extremity trauma, a variety of different things. And I've just took a couple of screenshots and put it up here for you to see a variety of different types of projects we do. Some, with pediatrics, some 3D printing, some finite element modeling, some experimental work, a variety of different things like that. We also develop implants. We also help develop new surgical procedures that are commonly used by our surgeons in the operating rooms. And actually, what I love about the work that we do is that in this area, we have a very direct impact on patient care. For not being medical doctors, we actually have a huge impact. Where medical doctors will see patient by patient one at a time, we actually are designing implants and developing different surgical procedures that are used by multiple doctors on multiple patients daily. So it's very nice for us. So here's one of the gruesome pictures. So some of the things that we work on is just basic fundamental understanding of how the body works. And so this is just a quick screenshot of a few pictures of an arm. Your arm, I don't know if you can see a picture, you can see me on the side of your screen, but basically, hundreds of times a day, your hand will do what's called pronation and supination. It's kind of the motion if you're trying to open a door, for instance. And there are two bones in your forearm, your radius and your ulna, that are connected by a series of ligaments that go across those. And if you become injured and you tear some of those ligaments, you can actually lose the ability to pronate and supinate your hand, to be able to move it in that motion. And basically what we were wondering was, what kind of effect does a loss of ligament or an injury to the forearm actually have on your ability to do this motion? And so we've designed a variety of different biomechanical studies. We have these high resolution motion capture cameras, something like you might see. I think most people are familiar with them, like if you're making video games where people are all set up with all these little markers all over their body, and these cameras are tracking them, and they turn those into video games. So we use that exact same type of equipment, but it's in order to enable us to apply loads the same way your arm would if it was connected to your body, and then track the motion of your arm and see how the bones are moving, how the ligaments are affecting that, and so forth. So that's one study. We also generally do things like resident training and evaluation. So for those who are not familiar with orthopedics or medicine, basically when you're done with an undergraduate degree, you can go to medical school. You go to medical school for 4 years. Those 4 years, you don't really specialize in anything. You kind of learn a lot about a lot of different things. And then you choose to go into some specialty, and where you typically will do what's called a residency, and it's basically a specialty in that field. And so in orthopedics, there's a 5-year program, a 5-year residency program. And in those 5 years, our residents have to learn all about orthopedics. They need to learn how to do surgery on the hand, on the spine, on your hip, you name it, pretty much everything except your skull, everything from the neck down, they're learning. And so we want to often be able to track how well they're doing. And most of the time, believe it or not, the residents are evaluated just by observation, basically by having the attending surgeons kind of look over them, watch them perform a procedure, and make sure that they're doing it okay. And so one of the things that I thought was really important is trying to figure out a way for us to actually quantitatively evaluate how they're performing the surgery. So are they applying too much load to that drill where they might accidentally plunge through the bone and come out of the other side and accidentally poke an organ or something like that? We don't want anything like that. And so we want these residents to be able to train outside of the operating room, but using actual surgical instruments that they would be using in the operating room. And so we've developed a series of surgical instruments that have sensors and other things that are applied to them that enable us to evaluate the surgeons using these drills, using these probes, a variety of different things to make sure that they're not going to harm the patient during their training period. And then one other thing that I wanted to talk about in biomechanics is that even though I'm in the Department of Orthopedics, we actually do quite a bit of collaborative research. So this is just a summary of a research project we did with Dr. Tabe. He was a cardiothoracic surgeon here at UNM. And basically on the top left here, you can see a picture. It's an X-ray of a torso, basically the chest cavity of a patient. See where those blue little lines are, or the blue little arrows are? They're showing these wires that have broken off of the sternum. The sternum is basically the bone that connects your rib cage in the front and your chest. These wires have broken off and they've migrated into the chest cavity of this patient. And so on the bottom there, you can see the different ways the surgeon, so for instance, if they're doing an open heart surgery, they'll take that sternum, they'll cut it right down the middle, and they'll spread that apart, and they'll do whatever procedure they need to do on the lungs or the heart, and then they'll close that back up, and they use these little wires in order to do so. And so Dr. Tabe came to me and asked, he said, I've been noticing that a lot of my patients are getting these wires, they're breaking and they're migrating into their chest cavity, and this causes way more problems than they did with the initial problems that they came in with. And so we designed a study that would enable us to evaluate how Dr. Tabe was putting the wires onto the patient's chest. And so you can see we developed this device that's up here on the top. It simulates kind of the muscle pull of the pectoral muscles. It allows us to position the synthetic bones over these load cells that are helping us figure out how much load Dr. Tabe is applying on these, because he thought, his hypothesis was that the patient's doing something wrong. The patient has to be doing something wrong that's causing these wires to break and migrate into their chest. And so I said, what if there's something going on in the operating room that you're just not aware of that might actually be causing these patients to have these issues? And he was nice enough and humble enough, I would say, to practice some of these procedures with us taking some, you can see we have motion capture markers on his arms and we have a load cell under it. You see him pulling up on that. You see how the table's moving underneath him. When he does this in the operating room, the patient's body actually lifts up off the table when he's doing that. And so one of the very interesting things that we were able to talk to him about was that when he was applying that very last process that's called the slack process, and he was pulling on those wires, he was doing something called yielding the material. So the metal was actually yielding. It was no longer in a state of perfection. And so once he had damaged, and I'm talking like 75% of the wires that were placed, and he placed almost 400 wires for us, about 75% of them had actually yielded before the procedure was done, even though they hadn't fully broken. And so what that basically allowed us to tell him was, hey, we need to come up with either a new way for you to put these wires in, or you might need to ease up a little bit on the patients. And we were able to evaluate quite a few cardiothoracic surgeons to do so. So anyway, that very quickly, that just provides an overview of my biomechanics and biomaterials research lab. I also run another lab. We call it the Ortho Team Lab. It's orthopedic tissue engineering, and we use additive manufacturing to do this. So in brief, what tissue engineering is. So tissue engineering is essentially bringing together biomaterials, usually in the form of scaffolds. And scaffolds can be synthetic or natural scaffolds. And you combine that with cells, preferably the patient's own cells, and other regulatory signals like growth factors or other mechanical or electrical stimuli, basically outside stimuli that will come together and enable tissue growth. And so you would use this in a situation, for instance, let's say a patient had an injury, or let's say a patient had a disease or defect. Let's say they had cancer and they had to have a portion of their bone removed, and they needed to have a scaffold implanted in there that you wish to regenerate that bone. This is the situation in which someone might use tissue engineering. So some of the things you might be familiar with regard to tissue engineering, you've got 3D reconstructed ears up on the top right there. The middle is a spinal vertebra that someone's 3D printed out of bone materials. And on the bottom right there, that's a lung alveoli that someone at Rice University actually just developed about a year ago that they're working on. So how does this relate to orthopedics and our interest in tissue engineering with orthopedics? So one of the biggest challenges in orthopedics right now is ligament rupture. So your ligaments basically connect bones to other bones, and they're always found at joints. So any joint in your body will have ligaments holding the bones together. And when your ligament ruptures, or let's say you have arthritis and someone needs to come in and do surgery, sometimes they can accidentally or intentionally injure the ligament in order to get in there to replace the joint or something like that. When that's done, the most common procedure that is used by an orthopedic surgeon to replace that ligament is something called reconstruction. And reconstruction doesn't necessarily mean that they're taking that ligament and kind of stitching it back together. It actually means most often that they're removing the ligament tissue that was there, and they're finding a tendon that's near the joint, and they're taking a piece of that tendon and they're using it to replace the ligament that they removed. So a tendon connects bones to muscle, and sometimes there are tendons in your body that are not quite as important as others, and so sometimes they'll use those. One of the downsides to that is that when they do that, the tendon doesn't act exactly like a ligament, so mechanically it doesn't have the same properties. Another problem is that you have to drill through the bones in order to fish that tendon through the bone, and then you use these screws to tack them down. And this does not replicate what an actual ligament and bone looks like. And so the bone ligament interface is actually one of the most complex regions of the body. And I'm not trying to minimize the complexity that it takes to 3D print a heart or a lung or any other organ, but the bone ligament interface is really complex because you've got this really hard bone and then you have this really soft ligament. But the ligament, even though it's soft, it has to be really, really strong because it has to keep your bones together at your joints, so you're not just kind of sliding around all the time. They have to be mechanically strong in tension because you're constantly walking or running or jumping, things like that. But there's also a very complex number of cells and other extracellular matrix materials. So basically proteins and other things that exist in that very, very tiny region where the bone and the ligaments transition to one another. And again, because ligaments connect bones to bones, you basically need to have this on both ends of the ligament, a transition from bone to ligament. So in my lab, we identified that there didn't exist a very good way to engineer a scaffold or tissue to reproduce this joint. And there also didn't exist any specific piece of equipment that could help us manufacture these type of scaffolds. And so with some research, what we ultimately realize is that some equipment will work for some things and others will work for other things. So for instance, 3D printing, which is what we've been doing a lot of, 3D printing is really great for reproducing geometries. So you want a bone, you can take a CT scan of a bone and you can create a three-dimensional model that looks exactly like that bone, and it'll print you something that's really, really strong under compression, just like bone. But it's not so great when you want to make ligament that needs to be pulled on, and sometimes it'll actually rupture when you're trying to 3D print a ligament. But there's this other procedure called electrospinning, and electrospinning allows you to produce these really small fibers, usually nanoscale fibers. And if you can control the electrospinning process, you can actually create really tightly packed, highly aligned fibers that will simulate ligament. And so essentially I said, we need to make some piece of equipment that can take these two different technologies and merge them into a single platform so that we can use this in order to make these bone ligament bone grafts that we would like. So we actually developed a device that would do exactly that a few years ago. And we have a patent that's currently in review on this, and it includes not just the technology itself, but the method by which you actually create these scaffolds and the scaffolds themselves. And so just so you can see on the bottom right here, this is kind of a generic view of what this might look like at a layer by layer buildup. So you would have these pink regions, these are the bones, the ligament is essentially the blue lines that bridge the two bones in between. These little squares that you see of different sizes, they simulate the different pores in the bones that might contain various cells, different cell types. So you've got bone cells, you've got ligament cells, you've got cartilage cells, and then you also have all of those other matrix materials that help to stimulate growth of those cells and regeneration of additional matrix materials so that you can produce this bone ligament bone scaffold that you can use for implantation. So just really quickly, my last slide on this topic, I just wanted to show you what it looks like under a high resolution image or high resolution scan, once we've actually used our device in order to make this. And I took a little, I blew up a portion of the prior image so you can see the different regions. So here you've got the end of this one bone, you've got the pure ligament region in between, and you can see we've actually controlled the fibers the way we want them to be so that they actually produce a really strong joining of the two bony ends. And you can see the various pores here that are in between that allow us to include cells and other materials in those pores. And then that middle region is just the transition region, showing how the ligament is fully integrated into the bony region and not just put in there with a separate, drill hole or something after the fact. So this is just a summary on the bottom right there. Those are two bones. That's the scaphoid and the lunate bone in your wrist. And that little white thing that you see there is our bone ligament bone scaffold and what it would look like if we were trying to replace that joint in between the two bones. So that's it. That's just a quick summary of the two labs that I run on campus, both in the Health Science Center, but they are totally staffed by engineering students. And so if anybody's interested, please feel free to send me an email. I'm happy to have you come and see what we do in the labs. So, so basically what most of you came for, an update on the 3D printed masks for the COVID-19 pandemic here in New Mexico specifically. So one of the things I'm most proud of and I wanted to talk really quickly about was the hurdles essentially that it took to just get us started. And I'm very proud of the fact that we managed to do all of this in barely over a month. On April 3rd, we received a notification of award that we had received some funding from the US Space Force. And that initial funding allowed us to purchase our first set of 3D printers and a lot of the infrastructure like the tables and chairs and 3D printing filament and things like that we needed in order to get this started. By April 7th, the university provost provided a special exception for student participation, assuming that we were able to abide by the governor's social distancing requirements. And so we were able to do that to get things going. By April 8th, all of our supplies and our printers had arrived and we began assembling. You can see on the bottom there, we have our printers being assembled, our tables being assembled, all of our infrastructure that started happening by April 9th. And by April 10th, we were able to begin production. And that's a picture of all of the 3D printers we had kind of lined up there that were printing our first batch of masks. By April 13th, we had a clean room set up. So it was set up very much like an emergency, like disaster shelter. As a matter of fact, the Secretary of Homeland Security said that he was really happy with the way we had designed it, so that because that's exactly how he would have done it. And so in there, we were able to bring some biosafety hoods from UNM main campus in order to do sterilization and packaging. By April 22nd, the UNM legal team had approved our memorandum of agreement, which basically required us to follow FDA guidelines for expedited production of the 3D printed masks that we were working on. And by April 24th, the state medical advisory team had given us approval to move ahead with distribution of our masks. But at that point, it was a little bit difficult. So even though it had been less than a month and we could distribute our masks, we had to do so basically by asking every single person who received one of these to have a notary and witness them sign this memorandum of agreement to make sure that they knew what they were getting, to make sure that they were given all the FDA guidance and everything that was needed. And to be honest with you, we at the time were really rushing to try to help get these masks to as many places as possible. People were really desperate, particularly in the northwest region of our state, and even crossing the border into Arizona. And so we went to the Secretary for Homeland Security, Kelly Hamilton, and we actually just showed him everything that we were doing and showed him our FDA guidance and showed him that we had received approval from the medical advisory team. And on May 7th, he actually gave us approval to distribute these masks in an unrestricted way, essentially under the guidance of the state. And so all we had to do, instead of essentially asking for permission, we just had to notify him of all the distributions that we were making, and that expedited things, and it really helped us get everything out there. And so this is what things look like right when we first started going in the launch pad. The launch pad is basically a space owned by Cosmiac. It's a Cosmiac facility. It's a research facility under the School of Engineering. We quickly became the COVID slayers. That was our hashtag on social media. So we had somebody even make some really cool decals for us. This became our new logo. We were the 3D mask makers and COVID slayers. And so we had a Facebook page and a variety of other things that we were able to share our efforts online with others and kind of solicit help in the form of donations and solicit help in the form of volunteers for our efforts. So this is what we decided to go with. So we use the NIH's, then this is the National Institutes of Health 3D Print Exchange, which was a place that was actually collecting a lot of different ideas about masks and face shields and other things from across the country. And there were tons of options. We had come up with our own designs, but ultimately we really liked this design by Christopher Wiles. He's a physician, matter of fact, in the Department of Orthopaedics up in the northeastern part of the country. And so we liked his design, but we made some modifications because one of the things that almost every single mask that was being made, they were making it with these hard plastic. It's like when you see a 3D printer, 3D printed parts, they're kind of hard plastic and they don't contour, they don't deform very well. So we decided that we wanted to take the money that we had received and invest in some higher end printers. We went with Lulzbot Taz Pro printers. These are about $5,000 a piece. And just to give you some perspective, you can buy a 3D printer for a couple $100s, but we wanted to go with these because they were durable. They had a very large build plate, so we could print a lot of masks at once. And we can print this material called thermoplastic polyurethane, which is a very flexible, if you can see my mask here, it's flexible. It allows it to contour to the face. We wanted to make sure there was a really nice tight seal all the way around so that the filters were providing protection, but also the mask itself is providing protection. Our filter cartridges, we just used more the rigid plastic material. You can see some images of that's me and Laura and a Girl Scout who actually donated a lot of hand-sewn masks that we were also distributing as part of this effort. And so she came to visit us and got a mask. And so you can see the filter cartridges on the front there. The filters that we used were called MERV 12 rated HEPA filters. They did not contain fiberglass, and we could easily buy these at Home Depot and Lowe's. And so it was really nice for us to acquire this quickly. And the straps that we used were latex-free rubber tourniquet bands, something that might be used like to draw blood. And we wanted them to be rubber because we wanted them to hold a nice tight seal up against the face. So this is just a quick video of what this would what this assembly looks like. So you've got the mask that we print, you've got the cartridge that we print, the filters we get, you snap it together, you put it up against your face with the strap. And this is just a picture of Laura with the mask on, and actually one of our 3D printed face shields that we had also been making at the time. So this is what our production flow looked like. So we had 3D printers that were printing our masks. We had other 3D printers that were printing our filter boxes. Those filter boxes and masks then went to a whole team of engineering students who were cleaning up these masks, because the filament actually sometimes makes them really messy. We wanted them to be nice and soft against the face. We didn't want there to be a lot of the things protruding and hurting anybody. And so they're there sanding and grinding and cleaning up all these masks. And then they put them in a staging area by color. Each of the colors denotes a different size. We were printing 4 sizes of masks at the time, small through extra large. From this staging area, we also had a whole bunch of volunteers from the health profession. So while a lot of our health professionals were, of course, in the hospitals working, there were a lot of other health professionals that were still, you know, they would go into the hospital, they would see everything that was going on, and then they really wanted to help even on their free time. So they were volunteering their free time to work in our that sterilized facility that we had. So there's some pictures of our mask and our cartridges that are in the UV hoods. So they were sterilized under ultraviolet radiation. You see some of our volunteers. These are paramedics, they're nurses, variety of different people from the health profession that would come in. They would get decked out in full PPE themselves that were being donated, and they would do all of our packaging, all of our assembly, putting the filters and everything together, snapping them together, and then vacuum sealing all of the completed masks into packages that were then ready for distribution. And then the last step of the process was essentially logistics and distribution. And so in the early stages, as I mentioned, the northwest region of our state and the western region of our state and the hospitals and the communities out there were really hit the hardest. So we would essentially print out various maps of the state, including specific COVID maps. You can see on the bottom left there, that's the Navajo Nation, separating the different regions by cases that were being seen at the time. And essentially that's how we were deciding early on how we would distribute our masks. And we were working with a number of community partners. We had some community members from PNM who worked with tribal relations there that helped us get in contact with all of the different chapters in the Navajo Nation. And we had a lot of volunteers that would help us drive these out. I just want to show you really quickly. It's a little video that I made. This, I would post things like this weekly on our Facebook page.
High School COVID hospital facility. We can still use some additional scrub caps. We've got 6 of them, and we've got some food donations for that location. We've got Zuni Home Healthcare. We got a shipment for them going out on Wednesday towards Gallup. Tomorrow we have the governor and lieutenant governor of Zia Pueblo coming, and so we have a nice donation of food for them. We can still use some more. They're coming at 10:30 tomorrow morning, so if anybody has any drop-offs that they want to bring to the Cosmiac facility, we can provide a location for that. We also have a delegate that covers 6 chapters up near the Shiprock Farmington area in the Navajo Nation, so we have a large donation for those six chapters. We've also got on Wednesday Fort Defiance, both the community as well as the emergency department out there that we can.
So I'm going to stop it there, but you can see that we have quite a few areas for distribution. We actually covered, all the way up to Shiprock, Farmington. We went into Arizona, we went to Chinle, a variety of different places. And so I would make these videos that we would put on our Facebook page for us to solicit any food donations, any water donations, anything else, because at some point we started with just the mask. And once we started going to these different communities, once we started going into these COVID hospitals, a lot of them were actually desperate for food in their area, for water, for hand sanitizer. The hospital specifically just wanted water and extra snacks for their staff members who were working, 24 hours a day in some cases. So here's a picture of some of our community and healthcare distributions. We had some notable ones on the right here. You can see this is the National Guard at the Mayamura COVID hospital that was set up in Gallup. This is the McKinley County Fire Department up on the top left that we distribute some masks for. And the bottom here, this is the governor, lieutenant governor, and delegates from Zia Pueblo that came to visit us. We've had people that were volunteering their own airplanes to fly donations for us across the country. On the top left here, this is Nota Begay III, the golfer, his foundation. We collaborated with him. We gave them a ton of masks that he helped us distribute within the Navajo Nation. On the bottom left here, we have a distribution that went out to Fort Defiance. And so this is one of the delegates from Fort Defiance area. In the top middle here, this is a delegate that came to us. That's the one that covered the 6 chapters up near Shiprock area. On the right here, this was us at Santo Domingo Pueblo. It felt like the entire Pueblo came out to greet us. It was amazing. Right here in this mask in the middle, that's Senator Martin Heinrich, who actually came with us on that distribution for the masks. We also worked with the New Mexico COVID-19 Emergency Supply Collaborative. So this is a collaborative that's still actively working. One of the things we quickly learned is that while we were able to distribute masks, places needed hand sanitizer, they needed gowns, they needed shoe covers, they needed anything that you could think of that was a PPE item. And so since we had the capability of making masks, we stopped making our face shields just so we could devote all of our effort to that, because we were the only ones in the entire state of New Mexico who were doing that. But there were other places that were also part of the collaborative, like New Mexico Tech, like CNM, like New Mexico State, who were able to supply other items. And so we began working together to form this collaborative in order to be able to distribute. So where our distribution started out with just masks, we were very quickly able to go down to New Mexico Tech. Here's a picture of us on the left at New Mexico Tech, picking up a whole bunch of hand sanitizer that they provided for us. That picture in the middle there are basically visors for face shields that were 3D printed at the CNM Fuse Makerspace. On the right here, this is a whole bunch of boxes. I think we had about 7,000 gowns that were donated from down south that we were able to get up to the Farmington area. So we expanded our distributions. I just have like 2 more slides. So on July 1st, we moved to UNM main campus into the STAM Commons room. So this is us transferring everything that we had. We scaled down our efforts a little bit as things started, kind of getting under control. And the Cosmiac needed to get up and running with their space applications too. So we were able to give them a little more space. At the time, just to give you some perspective of what we were looking at, on the top left there, from about January to June 17th, those were the cases in kind of some of the highest hit areas. You can see the dark green on the top left there, McKinley, San Juan areas. Those were the places we had been focusing most of our attention. You had 2,900 cases in those months. You had 2,100 cases in San Juan. You only had a little bit in Doña Ana County of 659, but right around June, going into July, you can see how that started to shift. So you still had quite a few confirmed cases in McKinley County at 37, but look at Bernalillo. Bernalillo jumped from about 1,700 cases by 2,000 cases in just a 1-month period. In Doña Ana County, we went from 600 cases to 1,700 cases in just a single month. And so we started shifting more of our effort to Bernalillo and Doña Ana County at the time. So as of today, we've 3D printed about 10,000 masks. We've distributed about 6,000 masks to the community, about 2,000 face shields. Our healthcare distributions, we've distributed about 2,000 masks and about 4,000 shields and 7,000 surgical gowns. We've delivered more than 1,000 gallons of hand sanitizer and well more than $5,000 worth of food, water, sanitary supplies, and so forth. And this is the way things look right now in New Mexico. There's, as of today, new cases, current hospitalizations, and new deaths. You can see in most cases, we're starting to go back down again. And this has actually allowed us to take a step back and kind of revisit our design to see if there are some areas for improvement. So you can see these were our initial filter boxes on the left here. They were kind of thick. They were made of a polylactic acid, which actually could melt if you left them in a really, really high temperature area. And so we wanted to slim down our cartridges. We wanted to make them out of a material that we didn't have to worry about getting deformed or anything like that. And we wanted to change the filter. So on the bottom left here, you can see the two filters we were putting in. We were gluing this filter into the front and then dropping this in. And the combination of the two were providing really high filtration capability. We started working with a local company called Marpac, and Marpac is now making us these filters. They're no more than 1 millimeter thick, and they actually have 3 layers. There's a woven and an unwoven cotton layer, and there's a polypropylene layer that's the waterproof layer. And so these now, they just drop into these slimmer cartridges, and you can see the difference on the left here. This is our original mask. This is our new mask design. The nice thing about just being able to drop them in and having a waterproof front is that if we needed to, if the time came that you know, this thing escalated again and we wanted to provide these to more healthcare providers, with them being waterproof and with them being fully sterilizable, once you remove that filter, you can wash them under soap and water, you can dry them, drop the filter back in, and you're good to go. And so we wanted to possibly redesignate these as surgical face masks, and by doing these changes, we actually are able to now go back under the current FDA guidelines for the COVID-19 pandemic and categorize these if we like. So that's all I have as far as summary goes. I just want to thank everybody who's helped, particularly our donors. You saw the screen with all of our donors that was running before I started my presentation. Thank them all. I want to thank them all for the funding, the food, the supplies. You have no idea how thankful people were. Laura Schaefer and Craig Keefe, they were my partners on this effort. Craig runs Cosmiac. Laura is his daughter. She's a flight nurse, and she's the one who really kind of put a fire in us to make sure we were hitting certain parts of the state that she was flying to and seeing that they were really struggling. And I won't go through all this. I know we're running out of time. So thank you all for listening. I really appreciate it.
Oh, thank you, Dr. Salas. Thank you for sharing your story and your incredible work with us. And I just want to say, as a Native American, like, thank you for providing those resources in such rural communities. Yeah, thank you. So now we'll start our question and answer portion. Remember, you can use the chat function. It's there at the bottom of your Zoom window. It's entitled Chat. We do have a question right here. I'm sorry. What advice would you share with young women interested in STEM fields, Dr. Salas?
Oh man, that's like one of my favorite questions. So I would say, please stay in the STEM field. And you know, I do a lot of outreach, and a majority of my outreach happens to be to middle school and high school females. And actually, thank you so much. You've given me the opportunity to put a plug in for an outreach program that I do called the Perry Initiative. And the Perry Initiative is targeting high school females who are interested in pursuing careers in engineering and medicine, because just like me, you can do both. You can become an engineer, you can go to medical school if you want, you can become an engineer and then go to grad school and work in a medical field. And so what we do is we host an outreach program every year where females get to come in and actually perform mock surgeries and to learn all the engineering things associated with the bones and the implants and things that we use for them. So I would just say, you know, anytime you have the opportunity to participate in programs just like mine, or ours, I should say, please do so. And, you know, come and visit us and reach out. You know, I do a lot of mentoring, and I'm happy to answer any questions you have in this area.
Awesome. Our next question, what makes UNM the right place for you to do your research?
Oh, that's a great question. You know, so I've been here for a long time through my master's and my PhD, and because of the work that I did outside of UNM and the work that I was able to do in collaboration with the Department of Orthopaedics, I did have other opportunities to go elsewhere. But, you know, as many places I went, not just the few that I've named, but others that I've had the chance to work at as well, one of the things I love is how closely tied the engineering department is with the School of Medicine. I mean, we have a leadership meeting monthly that brings together the leaders of the School of Engineering and the School of Medicine, particularly the research leaders, to talk about ways we can improve, you know, some of the things that we see in the clinic, in the hospitals, whether it be through designing new implants or designing new surgical procedures. I personally teach a class called Biodesign that actually helps students learn how to build and design these things for the hospital. And we're actually addressing very specific needs in our hospital. And I love that. That's actually something that you don't find everywhere, even at some of, these very, very well-known institutions, so that there are these different departments, but they're not always as integrated as ours. So I appreciate that.
Cool, thank you. Our next question is from Sierra. She says, with your knowledge from this opportunity, how would you address comments stating masks are not necessary?
Masks are not necessary. Oh goodness, I don't know how to respond to that. I personally believe that social distancing and masks are necessary. I follow the science. I actually follow it very, very closely. And, there is plenty of research out there showing how far particles can travel in the air. I mean, I know this is kind of a silly example, but the other day it was really windy out here, and I was walking from North Campus to Main Campus, and I passed the duck pond, and the fountain was on, and I was very far, like more than 100 feet away from the fountain, and you could still feel just the water hitting you. And that's just water and wind from the fountain. When people are talking, and you're generating a lot of saliva and other things. And so I really do believe that wearing a mask is limiting those particles, and particularly, that the research has shown that the particles themselves and the droplets themselves are what is spreading COVID. I really do believe that wearing masks and social distancing is helpful.
Okay, our next question is from Carol. Does UNM have opportunities for undergrad research?
Absolutely. There are quite a few opportunities for undergraduate research. Particularly, I was just talking to Yadi in the ESS program, and also it's a collaboration between electrical engineering as well, and they're working on a program to help encourage undergraduate researchers work in this area. There's the MARC program. There's prep. I'm sure that one of the people that's connected right now in ESS can probably name about 15 other programs that we've got going on that can engage undergraduate researchers in this area. So I encourage you to go to ESS and talk to them if you're interested. And if you're interested in biomaterials or biomechanics or tissue engineering or anything like that, I'm sure they will direct you to me. If not me, to anybody else in the School of Engineering that can help you.
I agree. There's a lot of research to be done. So Elsa and Yade have actually posted resources in the group chat for anybody who's interested or who would like to further know about that. Our next question is from Jack. Dr. Salas, considering all the obstacles that you had to face during the pandemic, how would you better streamline the distribution chain for future crises?
Yeah, I think I have never been so involved in politics in my life as I was at the start of this effort. I've met every senator, every state representative. I didn't speak directly with the governor, but I was pretty close. But that entire process of trying to bridge between the university and the state, and of course making sure that UNM was protected, because the last thing we wanted to do was get anybody in trouble or harm anybody with anything that we were making. That was some of the biggest hurdles. But I wouldn't say that I would not do that. I think that all of that was very important. It actually helped us make sure that we were meeting guidelines by the FDA. It helped us make sure we were meeting legal guidelines. And it actually helped us, every person we spoke with led us to another person that might be a little bit higher up in the chain, and actually helped, really get us to this point. And I don't think we could have done it any faster than a month. I think a month was pretty amazing. And so, if we had to do this all over again, the fortunate thing would be that we've already done all that stuff, and we could basically just go, the only thing we would need to do is go back to the state medical advisory team and say, hey, we now want to reclassify these as surgical masks. Please approve this, make sure we're meeting FDA guidelines, and go back to the Secretary of Homeland Security and say, hey, we're going to resume distribution, and we'll just let you know, where we're taking these and how we're distributing them. So.
Great, thank you. So Marissa says, thank you, Dr. Salas and your team for all your hard work towards all your efforts. You were mentioning the material the masks were made of. What are the lifetimes of these masks? Additionally, what happens to these masks after that point? Can they be recycled?
Oh yeah, that's a very, very good question. So we're starting to use PETG or PETG materials, which is completely recyclable for all of our filter cartridges. They also have a higher melt temp, so it's called the glass transition temperature, which is the point basically at which it can start to deform. And so the nice thing about that is that we were initially worried with our PLA material that if someone left it in a hot car or something, they were no longer able to use their mask, even though it was fully functional. And so these masks here, I'd say the weakest link in these masks are basically the rubber bands that we have around them. They will bust with repeated use, so we're providing replacements all the time. And the filter cartridges, we're recommending about a 3-month replacement, and that's based on the manufacturer where we receive the mask from. They do testing and they recommended a 3-month replacement for it. Otherwise, the other masks, I'd say if they start if they get squished, they'll get deformed and they can't be used. But generally speaking, we've had no one have any concerns or complaints about them, falling apart or breaking or anything like that. So I have yet to see the end of the lifetime to these masks, so I can't give you an exact answer. But that's a good thing. So we've been going for 5 months now. So they're going strong. The mask that I have here, I've been using this exact one since April. So going well.
Wow, that's awesome. Okay, we have one from Kenneth. Thank you so much for your assistance to all of New Mexico. My question is, approximately how much did it cost to manufacture each mask?
Oh, that's the best thing about this. So our masks, so again, we're not calling them respirators because we are not certified to call them respirators, but they function very similar to a respirator. The masks themselves complete, especially now that we've streamlined the process, we can make an entire mask filter cartridge, including the filter bands and everything, for about $2 a piece. And considering they're reusable and base sterilizable and can be used for a long time, that's actually a really good price for this. The filters themselves, we've actually managed with this new filters to also reduce the cost of those by half price. And so the price, if you look at respirators, you're talking on the order of, at minimum, maybe $50 for a respirator that you can buy at Home Depot that works similar to this. But most people are buying disposable masks. And so disposable masks, it probably costs about $20 a box of 10 or so, a box of 20. So we actually have really good price for ours not being disposable.
Wow, that's really great. If nobody else has any further questions, I think we are going to wrap this up. Does anybody want to get in any last questions before we? All right. Well, thank you, everybody. Thank you to all our guests, and a very special thank you to our donors who have supported the work of Dr. Salas. Our next talk in the Engineering in Action series will be in early October, and will focus on how drones are being used in faculty research and an exciting new space in development for that research. We look forward to seeing you again on October 2nd at 3 p.m. Thank you again for joining us, and go Lobos.